Good. First of all, I would like to thank the organizers of this conference, and would like to please excuse me. Because I've got a cold and had no power to prepare slides, so I will follow my paper pages, and I hope that the explanations will be also with the same quality as with slides, and will be understandable for you. Okay, so today this talk is very close connected to the previous talk. So we talk about a system, heterogeneous system that looks like this one. Like in the previous talk, we have one common queue. We have several heterogeneous servers, and typically, so the customers arrive according to a homogeneous Poisson process with a rate lambda. The JSON server has an exponentially distributed service time with a rate mu j, and the server j is called an available server if it is idle. And we also assume that the service of customers is assumed to be without preemption. That means a customer being served on a server cannot change it. This assumption is very important. Otherwise, we have no sense for some optimal policy or threshold policy. So the interarrival and service times, we, as usual, assume to be mutually independent. Also, additionally to the standard definition of interarrival or service times, we have additionally a cost structure that consists of operating cost Cj per unit of time for busy server j, and holding cost C0 per unit of time for any customer waiting in the queue. And we enumerate the server in such a way that we have decreasing ordering for the service rates, and increasing ordering for these values. We have called these values the mean operating cost per customer for the JS server. Why did we do we need this ordering? Because according to this ordering, it is possible to prove some monotonicity properties of the optimal policy, especially threshold structure. If we use another ordering, then we have some problems in theoretical proof of these properties. Okay, so typically, the problem, a general problem, consists in optimal allocation of a customer that has arrived to the system, and the controller must allocate this customer between the servers that are heterogeneous, not only in intensities, service intensities, but also in service costs. And additionally, we have a holding cost that also influences somehow in this allocation discipline. In our previous jobs, we have shown that in this case, the optimal policy must be of threshold type. I have marked these threshold levels here. This is the numbers of customers in the queue when we have to switch or use the certain server. For example, Q2 means that if the first server is busy, the second one must be used whenever the number of customers reaches this level and higher, and so on, Q3, Qk. The first server, that is the most efficient one, must be, it is possible also theoretically to prove, must be used whenever it is free. That means threshold level for the first server is always 1. Okay, so that means this condition we take into account. But now we have a problem. Not really a problem, but the motivation, searching for the optimal values, Q2 and so on, Qk, by direct minimizing the average cost function can be expensive, especially when k is large. For example, when k is not very large, it is possible to rewrite this problem in terms of matrix analytic solution that was done in previous talk. And in this case, we can derive the cost functional in explicit way, and then to use either direct search method for minimization or some numerical methods to find optimal values for the threshold levels. To calculate the optimal threshold levels can be used also the policy iteration algorithm. It's a very powerful tool which can be used in terms of dynamic programming approach. But this approach has also some certain limitations. For example, converges problems, especially in case of heavy traffic case. Also problems with dimensionality and so on. So the contribution of this paper is twofold. First, we provide a simple heuristic solution for some suboptimal policy in order to avoid the search of the optimal one by numerical methods. And it is suitable for any number of servers in the system. And second, we want to investigate the possibility to use the data generated by policy iteration algorithm or by some other method to provide a prediction for the optimal threshold levels with artificial neural network. So that means we need some algorithm that somehow solve optimization problems, maybe for some sets of parameters. This set of this data we use as for testing phase for neural networks, and then we can study by verification stage if it works or not. So that is the two main points in our paper. Okay, so the formal things connected with description of Markov decision problem I don't want to explain in detail. It is clearly explained in previous papers or in several books, for example, Kuterman or Rykov. So what is interesting here, I just want to a couple of words to say about this policy iteration algorithm that consists of two main parts. So the advantage of this algorithm consists of the following. So we construct a sequence of improved policies. We don't need to enumerate all possible threshold levels or all possible policies to calculate the optimal one. We need to select some initial policy, and we solve a system of linear equation for so-called relative value function. And as a result, we obtain for this given initial policy as a solution. Additionally, we obtain the value of our cost function. Then at the next stage, we can improve this initial policy and find the policy then for which this value, this average cost, will be lower. And then we compare the policies. If they coincide, we say that we have found the optimal policy. If not, we have to return and solve the system of linear equation, but for the new policy. Of course, this new policy will influence the transition rates. Yes, it must be taken into account. Then we solve this system of linear equations and again obtain the improved policy. And step by step, we get the sequence of improved policies until the optimal one will be found. So the number of steps that are required to find the optimal policy with a policy iteration algorithm is non-comparable with the direct search method, of course. Okay, and we use this method to get a sequence of data. So here I have shown the format of our data. It looks like a list where here we have a certain system parameters and the corresponding optimal threshold levels. So that means we evaluate for different combinations of system parameters. It can be done with some step, or randomly we can select these values. So we generate a data. So some elements of this data are illustrated here in this example. But we have, of course, much more elements in this list. Okay, now next step, we want to avoid the usage of any numerical procedures to calculate the optimal threshold levels. This heuristic solution is based, so we use in this case a simple and rather rough deterministic fluid approximation of the queuing process. It's not the same like a classical fluid queues here, because here we are interested in a number of customers to the certain time. Yes, and here this fluid approximation I can explain in the following way. We have to compare, for example, we are looking for threshold level for the case server. That means the first k-1 servers must be busy, and we have two possibilities. Either we put the customer, the new arrived customer, to the queue, then we have qk customers in the queue and k-1 customers in the busy servers. Or alternatively, we can put this new customer to the case server, and then in the queue we have one customer less. In this figure 2, so in this figure, the queue lengths are labeled by A if we have a queue length qk, and by B if we have a queue length qk-1. If the queue dynamics corresponded to the deterministic fluid, it would decrease at the rate the sum of mu j from 1 up to k-1 minus lambda. So with this, of course, it is very roughly speaking, will be decreasing in this rate, the number of queues, number of customers in the queue, but we can roughly accept this one. Okay, and when this rate is maintained until the queue is empty, it occurs respectively in points D and in points C. This is the time that is required to reach, make the corresponding queues empty. And the total holding times of customers in a queue with the lengths qk and qk-1 are equal, obviously, to the areas of these triangles AOD and BOC. So, and this can be written in this way. The mean operating cost we have additionally to take into account the mean operating cost of the first k-1 service until the queue is empty, starting from state x0, is equal to this one. Of course, it is mean operating cost for a certain server multiplied by the probability that the certain server will be empty. So that means we get the following item. And for when we start from state epsilon y0, it is equal to this one. And according to a specified deterministic fluid schema, we can formulate the following proposition, that the optimal threshold for the K-SOA can be written in this form. How it can be derived? Quite easy. So we have to compare the overall average system cost with respect to our two possible states, x0 and y0. And if it is optimal to allocate the customer to the K-SOA, it must lead to reduction of the overall system cost under fluid schema. So that means this inequality must hold. And now we have to calculate the overall average system costs. We use the times that we have already evaluated, the total holding times of customers in the queue multiplied by the cost per unit of time, waiting costs. This is the term for the usage of servers, and the rest costs for this state that we obtained. And for the state y0, where we use the K-SOA, it is almost the same, with one exception, that here we have the term for the K-SOA, the mean usage cost of the K-SOA, and here we have coefficient QK minus 1. If we simplify this inequality that we have proposed at the beginning, so we can obtain the situation that the K-SOA must be used whenever the number of customers is higher as this threshold level. It states for the whole part of the number. Okay, in next example, we want to check the quality of this heuristic schema. We select randomly from the data set. You remember, it's a data set that we have generated with policy iteration algorithm, and evaluate with heuristic schema the corresponding thresholds. Here, these are thresholds we use in this example, queuing system with 5 servers. That means we need to estimate threshold levels for the second, third, fourth, and fifth SOA. And we illustrate the quality by confusion matrix. In confusion matrix, each row represents the instances in a predicted value, while each column represents the instances in an actual value. And of course, in ideal case, the matrix must be diagonal, but of course we have fluctuations and deviations from the real values. But nevertheless, if we calculate the accuracy, that is percentage of elements from the data set that coincide with the real results, we see the following results. And if we allow that the thresholds can vary by at most 1 plus minus 1, because it almost has no influence on average cost function, then the accuracy is getting even more higher. Okay, so that means almost 97% we have a quality of prediction. Okay, and the last part of the paper is dedicated to artificial neural networks because I wanted to check if it can be used. It is very interesting approach because we can, using artificial neural networks, we can reconstruct some areas for the optimal thresholds if we cannot, for example, for some reasons, calculated by some other methods, or it requires a lot of time. For example, the parameters which correspond to heavy traffic keys. Yes, and here we use multi-layer neural networks. 70% of the same data, which was not used for heuristic solution, is referred to as training data, and the rest of this S is a validation data. We train a 6-layer neural network using an adaptive moment estimation method and the neural network toolbox in Mathematica of the Wolfram research. And then we verify the approximated function. So the results are summarized also by means of confusion matrices. And in the last table, we have accumulated the accuracies, the exact accuracy and accuracy if we allow the deviation for the thresholds plus minus 1. And we see that in this case, the results are even better. We have tried the algorithm. This algorithm was run many times on samples and networks with different sizes. And in all cases, the results were quite positive and indicate the potential of machine learning methodology for optimization problem in the QN theory. And finally, I want to say that when we are analyzing and comparing the results obtained by classical algorithms of the Markov decision theory and by supervised learning, we may conclude that these methodologies can be seen as complementary rather than competitive. So thank you for your attention.
Thank you so much, Dima. I guess there are some questions because there were some similar topics. So maybe some participants will address the questions.
May I ask, Alex?
Yeah, please do.
Dima, I'm happy to hear it from you, first of all. And my question is, please comment one more time why you need some approximation when you ask if have algorithm which gives optimal solution. Please clarify this point again.
The problem is that the policy iteration algorithm converges not for all possible values of system parameters. For example, on the boundary area, if we have heavy traffic, or in some special cases, I have also found that for some special parameters, it doesn't converge or converge very, very slowly. So in this case, we obtain the holes. Yes, the areas where we have no solutions. And in this case, these neural networks can help.
Oh, okay, thank you. And now it's clear. Yes, so it is actually complementary approach.
Complementary. Therefore, I have said finally that it is complementary rather than competitive.
Okay. Thank you. Thank you.
Any more questions, please? Well, then, thank you again. Thank you so much for your interesting talk.